In this video, we'll go through some examples of when you can substitute and when you can't. And just disclaimer, you really need to practice lots and lots of these, and I'm only doing like a couple examples in this video. So before you watch this, maybe go to the Khan Academy and Patrick JMT sites that I have on this website and do some examples with them. Make sure you're watching all the Study Forge videos and doing practice problems on Study Forge. To get good at this, you have to practice a lot, frequent practice over and over again. Okay, so let's do which one of these can be used substitution on. So one of these integrals requires substitution to evaluate. One can be evaluated with a simple formula, no substitution required, and one cannot be evaluated by hand. Which is which? All right, well, let's start with the first one, this one. So now you have to be careful because, well, first of all, notice that you have a quotient here. And right away, you should be thinking, I can't integrate that because there's no quotient rule with integration. The last section, hopefully you spent a lot of time in 504 practicing integrating with all the formulas. There's so many of them. So because there's a quotient here and we can't rewrite that in any way, well, we can to help integrate it, but let's get to that. You should be thinking that there's something that we need to do here possibly. However, Um, this is an inverse trig one. Those inverse trig ones are tricky. You're gonna have to make sure you look at those and memorize those. If you're an AP student, you have to memorize all of them. I'm so sorry. So notice that you have two squares being added in the denominator. When you have squares being added in the denominator, it's actually the inverse trig formula for integration, which is 1 over a. A in this case would be 3 because it's going to be the number that you're squaring to get the 9. And then u over a. U is x in this case. A is 3 again. So we can literally just plug this right in. This is the one that is a simple formula, no substitution required. So we can rewrite x squared plus 9 like x squared plus 3 squared and plug that right in. So that one's tricky. And it was mainly because there was just a 1 in the numerator. But the other two, they have x's in the numerator, and that causes more trouble. And if this was a 1, or it could have been a 10, or any constant, because you can pull a constant out. Let's say this was a 10 for a second. Well, then this would be 10 times all of this stuff. You would just take that constant right out. Okay, so if it's any constant on the top, you can factor it out in the front and multiply your answer times that constant. But as soon as you have x's, now we have issues. So let's look at the next one. So this one, quotient, it doesn't fall into our pattern of inverse trig this time. So let's try substitution and see what happens. When you use substitution, a lot of times it's guess or check at the beginning, especially when you're first learning. You pick something to equal u, and then you take the derivative of it. A lot of times the u is going to be like the innermost piece of a function, like an exponent or inside of a radical, the denominator. So let's do the denominator in this case. We say u is equal to x squared plus 9. So the next step is to take the derivative of u with respect to x, which would just be derivative of u with respect to x equals 2x plus 0. And now you can treat this like a fraction and multiply and get that dx on the other side. So now what you do is you look at your integrand here and notice that we have this taken care of. This is our u. We're going to replace that piece with a u. We still have an x and a dx that needs replaced. That's why it's called substitution. We have to substitute everything. We have to make sure everything has a spot and there's no leftover pieces, nothing extra. So in this case, we have an x and we have a dx. And we have that right here. We have an x and a dx right here. We just have a spare 2 involved. So you can actually divide by a 2. You can divide by a constant and bring it over here to the 1, or make it 1/2 on the other side. So it's really 1/2 du equals x dx. So now this is my u, so that's okay. I've taken care of that. And now this x dx, and I could say this because x is in the numerator. If I wanted to, I can rewrite this like this times x dx. It's the same thing because when you multiply fractions, it's top times top, bottom times bottom. So that x is right there. So now this is the same thing as 1 over u, and now my x dx is equal to this, 1/2 times du. So I can rewrite this, and everything has a spot. Nothing is extra, nothing is left over, nothing is missing. We are good to go. This is now 1 over x squared plus 9. Just rewriting this again so it looks prettier instead of in my handwriting. That's going to be my 1/2 du here. So this is the 1 over the u, 1 over u, 1/2 du. Everything has a spot. And now when you integrate and you have a constant, everything's being multiplied here. We can pull that out. Constant comes out. Looks like this. Now this right here, this is integratable. Is that a word? We're going to go with it. So now think about if you have 1 over u, that's a derivative. What function has a derivative of 1 over itself? That is the natural log. And because we have an indefinite integral here and here, we don't have a and b, then we have to add that plus c. So this is 1/2 times the antiderivative of 1 over u, which is natural log. This is the derivative, the function. If you have f of x equals the natural log of x, the derivative of that is 1 over x. So anytime you have 1 over u to the first power, it only works for the first power, because if it was 1 over u squared, you can rewrite that like this and now use the power rule. So be careful. This only works when you have to the first power. It's the natural log. Okay, let's get to this third one. This must be the one that cannot be evaluated by hand. Oh, I'm sorry. Before we go, I got ahead of myself. This u, before you move on, like if we'll do one with limits of integration, we'll cover what to do with the u. But if it's an indefinite integral, go back and plug u back in. Make it back to the x's. So u is equal to x squared plus 9. Our final answer is going to be the natural log of x squared plus 9. And I dropped these absolute values. Technically, inside a log, it has to always be positive. So notice that x squared plus 9 will always, always, always be positive. That'll always be positive because you're just going to square whatever you end up putting here for x will come out positive because of the square, and then you're adding 9 to it. So I don't really need those absolute value symbols anymore because it'll always be positive based on that expression. Okay, I got excited because I was ready to show you this one. Let's do this. Last one. So this is obviously going to be the one that doesn't work because this one was the simple formula. It was the inverse trig one, which is the sum of two squares here. This is the substitution one. This one won't work. So let's say we don't know what to do. We try u equals x cubed. So then if you take the derivative of that with respect to x and then multiply by the dx, you want to get the dx with the x on the same side. Notice that it doesn't work. Like we have this is taken out, we've got u right there, but we have this x squared. X squared plus 9 is an expression that can't be played with. It's together. That addition makes them close friends. They can't be separated. And it's not like this case where the x and the dx were both in the numerator. So this doesn't quite work out. Like we still could divide this 3 over here and you're left with x squared dx, but we don't really have, this is no good. This does not work. If we did what we did before, where we made the denominator our u, and then we did the derivative of u with respect to x, I'm going to bring that dx over right away, and then divide this by 2. This is the same thing that we did for the previous example for the middle one. Well, oh, whoops. Whoops, whoops, whoops. Ignore that. Okay, so we would have this taken care of. That's our u, but notice that we have an x dx and there's x cubed up here. So if I tried to use substitution, I would end up with the 1 over the u, and I would have an x squared, and then I could have my x dx, because you have to make sure that this x cubed gets completely replaced. And this would be my 1/2 du right here. So it would end up being 1 over u. There would be an extra x squared. It wouldn't work out. I can't have that. I can't have any extra stuff. Everything has to have a spot and completely replaced. So this is the one that cannot be evaluated by hand. Well, technically it could. If you're a BC student or you go further into calculus, you could actually use long division to simplify this integrand, if you remember that from pre-calc, and then you could integrate it by hand that way. There are other ways of doing this one, but in this course, we can't use substitution.